19.455 degrees north, 266.406 degrees east. That is a set of lunar coordinates, and as of the middle of July, an astronomer working out of Maine has calculated that a 5-story piece of rocket hardware will strike that exact patch of ground at 6:34 and 33 seconds coordinated universal time on August 5th, plus or minus a few seconds. Not roughly, not sometime this summer, a time down to the second and a location down to a fraction of a kilometre. For an object nobody is steering, tumbling in the dark, a third of a million kilometres away. I want to be precise about what makes that strange. We are extremely good at predicting things we control, a spacecraft on a programmed descent, a rocket on a guided trajectory. This is not that. This is 4,900 kilograms of abandoned Falcon 9 upper stage, dead in space for a year and a half, and we can still tell you to the second when it's going to hit the moon. And yet, for all that precision, there's a piece of this event that remains a complete unknown, whether anyone, anywhere, will actually see it happen. Every previous object we know of that has struck the moon in the modern era has done so either in darkness, on the far side, or both. This one might not. This might be the first time a predicted lunar impact happens somewhere we can actually watch. In the next few minutes, you're going to understand exactly what this object is, why it's the moon and not Earth on the receiving end, what decides whether it's visible, and what the honest odds are that anyone gets to see a 5-ton piece of American rocket hit the moon in real time. Start with what the object actually is, because space junk undersells it. On January 15th, 2025, a Falcon 9 lifted off from NASA's Kennedy Space Center, carrying 2 payloads to the moon, Firefly Aerospace's Blue Ghost Mission 1 and Japan's Hakuto-R Mission 2, called Resilience. The rocket's job was to get both landers out of low Earth orbit and onto a trajectory that could reach the moon. Once it had done that, everything separated. The 2 landers, a payload canister that had held them together, and the upper stage itself, catalogued as 2025-010D. Blue Ghost went on to make history. It touched down at Mare Crisium on March the 2nd, 2025, the first fully successful commercial moon landing, and it went on to run the longest continuous commercial operation on the lunar surface to date. Resilience did not get there. 90 seconds before touchdown on June 5th, a laser rangefinder failed and the lander went into the ground instead of onto it. The payload canister that had carried both of them re-entered Earth's atmosphere on March 15th, 2025, burning up somewhere near the Argentina-Chile border, probably seen by no one. That leaves the upper stage. Unlike the canister, 2025-010D never came back down to Earth. It settled into a long, lopsided orbit as close as 220,000 kilometres from Earth at its nearest point, out to 510,000 kilometres at its farthest, looping around roughly every 26 days. For comparison, the moon itself sits at an average distance of about 385,000 kilometres. For a year and a half, that orbit has been drifting, and the object has made a few close passes by both the moon and Earth without incident. On August 5th, that changes. The orbit of the upper stage and the orbit of the moon intersect, and this time, both will arrive at that intersection point at the same moment. Here's the part that should surprise you. Nobody was steering this toward a lunar impact, and almost nobody was even watching for it, at least not on purpose. The object is too far away for military radar to do much with. Radar works by bouncing a signal off a target and catching the echo, and the strength of that echo falls off with the 4th power of distance. An object 400 times farther away, which is roughly where the moon sits relative to low Earth orbit, returns a signal that is 400 squared again, or about 25.6 billion times fainter. Radar is superb for tracking gloves and tool bags astronauts have lost in low orbit. It is nearly useless out here. What actually caught this object were the telescopes built to find something else entirely. Asteroid surveys, networks of observatories scanning the sky every night for near-Earth asteroids that might someday threaten the planet. That's their real job, planetary defense. But in their images, a tumbling rocket stage and a small asteroid look almost identical. Both are slow-moving points of light. So the surveys pick up junk like 2025, 010D, whether they're trying to or not, and over many months, observatories in Mississippi, Utah, Beijing, and England, among others, quietly logged well over 1,000 data points on this object. By late February of this year, that had grown to 1,053 recorded observations. That data went to Bill Gray, an astronomer who runs Project Pluto and Built Guide, a piece of tracking software used by professional and amateur observers worldwide to keep tabs on asteroids and satellites. In September of 2025, Gray's orbit computing software chewed through the accumulated observations and spat out something unexpected: a projected impact with the Moon on August 5th, 2026. This wasn't the first time Gray had made a call like this. Years earlier, he'd identified a different piece of space debris on a lunar collision course, and that discovery drew far more public attention than he expected. This time, he built a page anticipating the same questions before anyone had to ask them. So why isn't this locked down to the meter yet if the tracking is this good? Because the physics of a rocket stage isn't just gravity. Gravity from the Earth, Moon, Sun, and planets we know to extraordinary precision. If that were the whole story, Gray could likely tell you the impact point to within a few meters. The complication is sunlight. Solar radiation pressure is an almost absurdly gentle force, but it acts on this object for months at a stretch, and it isn't fully predictable because the upper stage is tumbling. As it spins, different faces catch the sunlight at different angles, sometimes reflecting it sideways rather than straight through. So the push is mostly away from the sun, but with an unpredictable sideways component layered on top. Picture a leaf spinning slowly downward in a light breeze. The average direction is down, but the tumbling means no two leaves land in quite the spot you'd calculate from a still fall. That's the leftover uncertainty in this prediction, not whether it hits, but precisely where and when. That uncertainty has already shown up in the numbers. Gray's prediction has been updated 3 times as new observations came in. Once in June, which moved the predicted time about 9 minutes earlier, and the location roughly 170 kilometres to the northwest of the original call, and again in mid-July, which shifted things by only about 10 kilometres and a couple of seconds. Each update has been smaller than the last, which is exactly what you'd expect as more data narrows the error bars. By the time August 5th actually arrives, Gray expects the prediction to be accurate to within a few dozen metres and a fraction of a second more bytes, because astronomers will be gathering data on this object almost up to the moment it disappears from view behind the lunar limb. That drifting 170-kilometre shift matters for one specific reason. It's the difference between an impact we can watch and one we can't. As of the most recent update, the impact point sits, in Gray's words, just barely on the near side of the Moon, the face we can see from Earth, close to the heavily cratered ground near the crater Einstein, right at the edge of the visible disk. A shift of even a little more in the wrong direction would have carried it around to the far side, the hemisphere no one on Earth has ever laid eyes on directly. That near miss of a miss is the whole tension in this story. We are not asking whether this object will hit the Moon. That part is essentially certain. We're asking whether the geometry leaves it anywhere we can actually watch. If it stays on the near side, as currently predicted, here's what an observer would be working with. The impact happens about a week after full moon, with the Moon a little more than half illuminated, striking ground that's in full sunlight rather than shadow. The upper stage will be moving at 2.43 kilometres a second, 1.51 miles a second, roughly 8,700 kilometres, or 5,400 miles an hour. There's no air on the Moon, so a Mach number doesn't strictly apply, but if you insist on the comparison, that's about 7 times the speed of sound. At that speed, a 4,900 kilogram object releases about 14.5 billion joules of kinetic energy on impact, the equivalent of roughly 3 tons of TNT, or about 15,000 sticks of dynamite. That is a genuinely large release of energy. What it is not, according to Gray, is dangerous to anyone. It doesn't present any danger to anyone, he told Space.com, though it does highlight a certain carelessness about how leftover space hardware is disposed of. Hold on to that phrase, carelessness, not catastrophe, because it's the most honest one-sentence summary of this entire event. Now for the branches, because there are genuinely 3 different outcomes still on the table, and they are not equally likely. The most probable outcome by a wide margin is the one that's played out before. No visible flash, nobody sees anything happen in real time, and the only confirmation comes weeks or months later, when a spacecraft orbiting the moon photographs a fresh crater. There's real precedent for that outcome. In 2009, NASA deliberately steered a Centaur up a stage into the moon as part of the L-Cross mission, hoping to kick up water ice for analysis by a trailing spacecraft. That impact was carefully timed to strike the unlit side of the moon, where large telescopes were watching for a flash. Nothing was seen. Bill Gray has pointed to that precedent directly, saying he can't come up with a strong reason this impact would be meaningfully brighter, even though, unlike L-Cross, this one happens in daylight. Part of the problem is speed. The flashes astronomers do occasionally catch on the moon come from natural meteoroids, and those typically arrive far faster than this rocket stage will, commonly around 10 kilometers a second and as fast as 70. According to Bill Cook of NASA's Meteoroid Environment Office, the faster an object hits, the more of its energy comes out as visible light rather than heat or displaced rock. At 2 by 43 kilometers a second, most of this impact's energy is likely to go into excavating a crater and throwing debris, not into a flash bright enough to see from Earth. The second branch, less likely but not dismissed, is that a flash is seen but faint, caught by dedicated observers with large telescopes trained on exactly the right spot at exactly the right second, but invisible to the naked eye or a casual glance upward. This is where the timing actually helps. For observers across the eastern half of the United States and Canada and much of South America, the moon will be up and it will be nighttime at 0634 UTC, which works out to the very early hours of August 5th on the East Coast. That's a genuinely wide footprint of potential witnesses with a clear line of sight, even if most of them won't be looking with the right equipment. The third branch is the one most people actually want, something visible without a telescope or close to it. Here the case is thinner, but not zero, because the impact point sits almost exactly on the lunar limb, the very edge of the visible disk. There's a specific possibility beyond a flash, an ejector plume. Material blasted outward by the impact could, in principle, rise high enough above the curve of the moon to be seen silhouetted against the dark sky beyond the limb, rather than lost against the bright lunar surface itself. Working from the impact energy and a rough model of how much debris the Chang'e 5 T1 rocket stage kicked up in a broadly similar 2022 impact, about 450 cubic meters, or roughly 1,800 tons of pulverized lunar material, the math suggests ejector could be thrown upward at perhaps 100 meters a second, rising for about a minute to a height of roughly 3 kilometers before falling back. At that altitude and that distance from Earth, the object would sit only about 1.5 arc seconds off the edge of the moon in the sky. Is an extremely tight gap, but not necessarily an impossible one for a good telescope and a patient observer. Nobody involved is confident this will be visible. Everybody involved thinks it's worth pointing a camera at anyway. There's a connective piece to this story that matters as much as the impact itself, and it's the reason Gray keeps returning to that word, carelessness. This isn't the first time a derelict rocket stage has ended up on a lunar collision course, and it won't be the last unless disposal practices change. A similar object struck the far side of the moon in 2022, later identified informally as a Chinese Chang'e 5 T1 upper stage, though the China National Space Administration has never officially confirmed it as theirs. The Lunar Reconnaissance Orbiter photographed the result a couple of months afterward. Not one crater, but two, roughly 16 and 18 meters across, sitting side by side. The leading explanation is that the object had a heavy rocket motor at one end and a heavy, undisclosed payload near the other, so it effectively hit the ground twice, milliseconds apart. This new object, 2025 Is-10D, carried two spacecraft to the moon, but doesn't appear to have the same kind of dense secondary mass. So the expectation is a single crater somewhere around 17 meters across and roughly 2 meters deep. The Lunar Reconnaissance Orbiter is expected to image it in the following months, and Gray has said he expects to be able to tell the LRO team almost exactly where in their images to look. The deeper pattern here goes back decades. During the Apollo program, the spent upper stages from Apollo 13 through 17 were deliberately crashed into the moon on purpose to generate small moonquakes that calibrated the seismometers earlier astronauts had left behind. That was intentional science. What's happening in 2026 is not intentional at all. It's a byproduct of orbital mechanics nobody planned for on hardware nobody steered. And the practice of simply leaving upper stages wherever their post-mission orbit happens to carry them is increasingly viewed inside the industry as something worth fixing. When the James Webb Space Telescope launched in late 2022, its spent upper stage was deliberately placed into an orbit around the Sun, engineered to avoid hitting Earth or the Moon for at least a century, and likely for thousands of years. More recent missions have followed that model. Gray notes that at least one more recent Falcon 9 upper stage, launched in November of 2025 for the Escapade mission to Mars, was placed on a Sun-orbiting trajectory as well, and that SpaceX reportedly wanted it that way. China's own recent lunar launches have shifted toward the same practice, a departure from an older pattern that left stages on paths that could eventually strike the Earth or Moon. The trick only works for missions with enough energy to escape into solar orbit in the first place. Most ordinary satellites aimed at low Earth orbit simply don't have the fuel margin for it. Avoiding a lunar impact turns out to be the comparatively easy problem. Avoiding the much larger volume of junk that stays close to Earth is a far harder one. Before we get to what to watch for on the 5th, we have to clear out the noise because any story involving rocket, moon, and impact in the same sentence draws a crowd of overreaction with it. The first claim making the rounds is that this represents some kind of hidden weapons test disguised as space junk. There's no physics or evidence behind that. This object has been publicly tracked since shortly after its January 2025 launch. Its catalogue number and orbital elements are openly published, and the prediction itself comes from an amateur-accessible orbit determination tool running on data anyone can pull from asteroid survey archives. Nothing about this trajectory was concealed, engineered, or aimed. It's a spent rocket stage drifting along the only path gravity and sunlight gave it. The second claim is that an impact this size poses a real danger to Earth, to astronauts, to future missions. On the danger to Earth question, there's simply no mechanism. The object is going to strike the moon, not us, and the release of energy involved, while large in human terms, is trivial on a planetary scale. As for the moon's other current residents, the risk isn't zero, but it is small and specific. Gray has said plainly that there's a lot of room between the predicted impact site and the nearest Chinese rovers on the surface, and that if he were operating a spacecraft in lunar orbit, he'd check whether it might be passing over that exact patch of ground at that exact second, and adjust if so out of caution rather than alarm. He's also been honest that the calculus will look different once humans are regularly living and working on the lunar surface, when a stray ejector field becomes a genuinely different kind of hazard than it is today with nobody down there yet. The third claim is really more of a concern than a conspiracy, and it deserves the concession it's usually denied, that space junk in general is becoming a real problem, and that this event is a symptom of it. That part is true, and it's worth saying plainly rather than debunking. Astronomers are increasingly worried about a sky that's never fully dark anymore, streaked by low-orbiting satellites in nearly every long-exposure image. There are documented concerns about metal particles from re-entering junk building up in Earth's upper atmosphere, and the far worse scenario, known as the Kessler effect, describes a runway chain reaction. Enough debris in orbit that collisions generate more debris, which causes more collisions, until a given orbital band becomes unusable. Nobody serious thinks we're close to that yet, but the trend line is real, and this Falcon 9 stage, in a genuinely small way, is a data point in that broader, legitimate concern, even while the specific event on August 5th remains harmless. So, what to watch, with real dates attached? The first is August 5th itself, 6:34 and 33 seconds UTC, give or take a handful of seconds, 2:34 AM Eastern Daylight Time, 11:34 PM Pacific, on the night of August 4th. In the days immediately before that, astronomers will keep refining their prediction using fresh telescope data. And by the time impact actually arrives, Gray expects the numbers to be locked down to within meters and fractions of a second, a level of precision that simply isn't possible today. If you want to try to see it yourself, the target is the sunlit limb of the moon near the crater Einstein in the pre-dawn sky over the Americas. The second checkpoint is whatever comes out of that morning's amateur observing effort. The flash watchers and plume hunters with telescopes already aimed at that patch of sky. Given the honest odds laid out above, the most likely outcome is silence. Nothing seen, no confirmation until later. But if either a flash or a plume is caught on camera, it would be a genuinely new kind of data point. The first time a predicted lunar impact of this kind has been captured happening rather than just found afterward as a crater. The third checkpoint sits months out. Imagery from the Lunar Reconnaissance Orbiter, expected to locate and photograph the resulting crater, following the same playbook that confirmed the 2022 impact. That's the one piece of this story that is close to a sure thing. Whether or not anyone sees the moment of impact, the evidence of it will be found and photographed eventually. So hold two things at once because both are true. The cautious mainstream reading is that this is a minor event, a 5-ton piece of forgotten hardware completing an unplanned, harmless collision with a world that's already covered in far larger craters from far larger impacts, on a surface where nobody currently lives to be at risk. Nothing about the physics here supports alarm, and nothing about the source, a public catalogue number, an openly shared prediction. A page built specifically to answer questions before they're asked, supports secrecy. And yet the attention-worthy reading is also true. We are, for what may be the first time, watching a predicted human-made lunar impact happen on the correctly lit, correctly facing side of the moon, tracked to the second by ordinary telescopes doing a job they weren't even built for, at a moment when cameras across 2 continents will already be pointed at the sky. Every comparable event before this one, the Apollo stages, L-Cross, the 2022 Chang'e 5 T1 stage, happened somewhere we couldn't watch, or in darkness we couldn't pierce. This is the first real shot at actually seeing one land. It might not happen. The honest odds still favour silence and a crater discovered later. But for the first time, we're positioned to find out in real time instead of after the fact. We will be tracking it.